let's look at some examples of using this existence and uniqueness theorem to analyze some initial value problems. So just as a reminder, when you have a first order differential equation with an initial condition, so a first order initial value problem, and you have an initial condition, if the function that is the right-hand side of the differential equation, if that function is continuous on a rectangle containing the initial condition on its inside, then there is sure to be a solution, at least one solution, so a solution exists. And if the derivative with respect to y of that function is also continuous on this rectangle, then the solution is unique. So it's sort of a two-part thing. First, we're going to check if a solution exists by thinking about if the function is continuous, and then we'll check its derivative to see if the solution is unique. Okay, so let's look at some examples. First example, let's figure out for this differential equation, for what initial conditions is this guaranteed to have a unique solution? So we don't have a complete initial value problem yet. What we're asking is, right, remember an initial value for a first order equation is just a point in the xy plane. And what we're asking is, for what points in the xy plane is there a single solution through that point? Right? That's what we're really asking. So let's use our theorem. We already have this equation arranged so that dy dx is by itself on the left-hand side. So the right-hand side of this differential equation is what counts as f of xy. So that's 1 over x minus 1 plus y to the 1/3. Okay, and we need to know for part 1 of our existence and uniqueness theorem, we need to know where is this continuous. So what could go wrong? So f continuous. What could go wrong with this formula, the formula for this function? The cubed root never goes wrong. You can take cubed root of any real number. But this first part with the quotient could go wrong, right? If the denominator is 0, that would cause a problem. And so x can't be 1, right? Because if x were 1, then we'd be dividing by 0. This function is continuous for any other point on the xy plane except points where x is 1. So let's just put that on our xy plane here. So as long as we stay away from this vertical dotted line where x is 1, initial value problems initial values in this region of the xy plane produce solutions to the differential equation. Now we don't know if those solutions are unique yet, but they're guaranteed to exist at least one solution through every initial value in this region of the xy plane. By this region, I mean all of the xy plane except this vertical line. Okay, so that's where solutions exist. Now let's look at where solutions are unique. So we need to figure out where the derivative of f with respect to y is continuous. So first we need to find what this derivative is. And remember, we're just going to treat x like a constant in this formula and treat y like the variable and take a regular derivative. So since we're treating x like a constant, this first piece that only has x's in it, this first term, just goes away when you take a derivative with respect to y. And then the second term, y to the 1/3, you can just use the power rule. So you get 1/3 y to the negative 2/3. And rewriting this a little bit, that's 1 over 3 times y to the 2/3. Okay, so we need to know where is this continuous. And Again, we can't divide by 0, so this derivative is continuous when y is not 0. Okay, so already we had to avoid this vertical line where x was 1. Now we have to also avoid this horizontal line where y is 0. And that will give us unique solutions. So we have unique solutions, unique solutions when our initial value, x naught, y naught, satisfies x naught can't be 1, because we have to avoid that vertical dotted line, and also y naught, or y naught can't be 0. So if either one of these conditions is not satisfied by our initial condition, then we are not guaranteed to have a unique solution. But for any point off of these two dotted lines, we're guaranteed to have a unique solution. So for every other initial condition, there's a unique solution that goes through that initial condition. All right, let's look at another example. Let's actually come back to our cooling example. So this was our cooling differential equation, and we had an initial condition. So I've changed our initial condition. Our initial condition is that capital T of 10 is 30. Is there sure to be a solution through this initial condition? And if so, is it unique? Well, we have a first order equation, and the derivative is on the left by itself. So we can use our existence and uniqueness theorem to answer these questions. This time it's not x and y, it's little t for our independent variable and capital T for our unknown function. So for the first part of our existence and uniqueness theorem, we just need to check where is this function continuous. So this function, I guess I should actually write it out. The function we're talking about is f of little t and capital T is minus 1 over 10 times capital T minus 20. And where is this continuous? Right? Where in the little t, capital T plane is this function continuous? Well, there's nothing that ever goes wrong with this formula. It's continuous everywhere. So for any initial condition, there is a solution for that initial condition. So solutions exist for all initial conditions. I'm going to abbreviate initial conditions. In particular, for our initial condition, 10, 30, solutions exist. Okay, and notice that I said solutions and not just solution, because we haven't checked yet if the solutions that we now know exist, we haven't checked if there's actually a unique solution. We're going to do that next. We kind of expect that there should be a unique solution because this is supposed to be describing a physical situation, and physical situations tend to have one possibility, as long as you ignore quantum mechanics. Okay, so let's check the second part of our existence and uniqueness theorem. First, we need to calculate partial f partial. Remember, what we need to take a derivative with respect to here is the unknown function variable. So that's capital T, not little t. And if we calculate that, we just get minus 1 over 10. And this is continuous everywhere again. So it's not just that solutions exist for all initial conditions, it's that unique solutions exist. So unique solutions exist for all initial conditions. And in particular, for our initial condition 10, 30, there is a unique solution. Okay, good. And that sort of satisfies our intuition that there should be one solution for a physical situation. All right, final example. Let's go back to this differential equation, which, remember, had these two solutions for the initial value y of 0 equals 0. So we had this piecewise solution that was 0 for a while and then sort of jumped up away from 0. And we had another solution that just stayed 0 forever. And in fact, there are many other solutions. So the question that I want to ask is, can this initial value problem have multiple solutions for any other initial conditions? So we started with the initial condition 0, 0. What I'm asking is, if we change this initial condition to x naught, y naught, are there any other initial conditions where there could be multiple solutions? Well, that's a question of uniqueness, right? We want to know, are there any initial conditions where we cannot guarantee uniqueness of solutions? So we need to check part 2 of our existence and uniqueness theorem, because that's the part that deals with uniqueness. So let's calculate partial f partial y. Right, take the derivative of this cubed root of y with respect to y. Cubed root of y is y to the 1/3. And so when you take a derivative of that, you get 1/3 y to the minus 2/3. And that's 1 over 3y to the 2/3. And this is continuous on most of the xy plane, but not the whole xy plane. This is continuous as long as y isn't 0. So if we draw a picture of the xy plane, to get unique solutions, our initial condition has to avoid this line y equals 0. Okay, so multiple solutions are possible. Multiple solutions are possible if our initial condition has its y value, y sub 0, be 0. Right? If the y value is 0, then we're on this dashed red line, and that is the place where we cannot guarantee unique solutions.